Now we're going to talk about adding and subtracting radicals. So adding and adding and subtracting radicals are like adding and subtracting like signs. So you know if we have, or like terms. So you know if we have 2x squared plus say 3x squared, this variables need to be the same for these to be like terms, and the exponents on the variables need to be the same. When those are exactly the same, then we keep the variable with its exponent and just add or subtract the numbers. So in this case, 2 plus 3. So this is the exact same idea, okay? So if I have 11 times the square root of 7 plus 7 times the square root of 7, well, these radicals both have 2 as their index, and it's 7 underneath. So they're like our x term in regular terms. These are exactly the same. So we just keep those and then add or subtract the numbers. In this case, 18. So this is 18 times the square root of 7. Okay? So one more time, just to be sure we get this. As long as the radicals have the same index and it's the same thing underneath, then these are quote-unquote like terms. So I keep the like term part and add or subtract the numbers. Okay? But what happens when the radicals aren't the same? So let's look at that. Oops, wrong one. Okay, so 5 times the 4th root of s minus 3 times the 3rd root of s plus 2 times the 3rd root of s plus 4 times the 4th root of s. Well, first of all, this term and this one are the same because they both have a 4th root of s. Okay, so I'm going to write the 4th root of s because that just stays the same. And then I add or subtract the numbers. In this case, it's a 5, a positive 5 and a positive 4. That gives me 9. Okay, so now I'm done with these two. And now this and this one are like terms because they are each the cubed root of s. Okay? So now I just add or subtract the numbers. So this is the -3 plus 2. That's an addition problem whose signs are different. So I subtract the numbers, keep the sign. Well, 3 minus 2 is 1, which I don't write, and then I just keep the sign of the bigger one. Now I cannot combine these two because it's sort of like trying to combine x and y. Because they have different indexes, they are different variables, basically. Okay? So they are not like terms. Let's just do some more. Okay? So if I have the square root of 45 plus 4 times the square root of 5, well, these aren't like terms yet because although both of my indexes are 2's, what's underneath is not the same. So let's see if maybe I can reduce the 45. 2 doesn't go into it, but 3 does. 3 and 5, 2. So that is 3 times the square root of 5 plus 4 times the square root of 5. Well, now they are like terms, so I keep the like term part and add or subtract the numbers. Okay? Let's keep going. Just do a bunch of examples. -5 times the square root Okay, so they all the radicals have squares in them, but not one of them has the same thing underneath. So let's see about reducing each one of these. 2 times 48, 2 times 24, 2 times 12, 2 times 6, 2 times 3, and the index tells me it's this, so this is going to be 2 times 2 is 4, times the square root 2 times 3 is 6, plus, let's do it with 24, 2 times 12, 2 times 6, 2 times 3. Index says 2 has to be in my group, so 2 times the square root of 2 times 3 is 6, and one more, let's try it with 54. So 2 is 2 times 7, 3 times 9, 3 times 3, so I've got 3 times the square root of 2 times 3 is 6. Now these are all like terms, so I'm going to keep the square root of 6. 4 plus 2 is 6 minus 3 is 3, and that's my final answer. So that's all we have to do is reduce all of these until, if possible, they're the same underneath the radicals. So plus 7 times the cubed root of 2. Okay, so these are not like terms, but let's see if I can reduce the 16. 2 times 8, 2 times 4, 2 times 2, and 3 needs to be in a group. That's what my index tells me. Remember how I've been saying all along, you've got to say that these radicals correctly or you won't know what to do. 11 times the cubed root of 16. Now we're going to bring a 2 out. What do you think is going to happen with that 2 and the 11? Because it's 11 times, it's 11 times 2 times the cubed root of 2, which is what's left. And then this, I know there's no cube root of 2. Well, not an even one anyway. Well, 11 times 2 is 22 times the cube root of 2 plus 7 times the cube root of 2. Now my terms are like terms, so I can go ahead and keep the like term part and just add or subtract the numbers, and my final answer is 29 times the cube root of 2. Okay, let's see. I'm just going to keep doing as many as I can here to help you guys out. Times the square, so 16k to the 4th times the square root of k minus 13 times the cubed root of k to the 9th. Well, there's nothing I can do with the first square root of k, so we'll just keep that. So 16k to the 4th times the square root of k. And let's see, 13. How many 2's, because my index is 2, how many 2's in k to the 9th? Well, there are 4. 4 times 2 is 8. And that leaves me with 1 left over. He has to stay inside. And now my radical parts are the same. And look at this. My variable parts are the same. So all of that makes this be like terms. K to the 4th times the square root of k makes it be like terms. So I just keep all that and just add or subtract the numbers now. So 3k to the 4th times the square root of k. Okay, let's try another one. So minus 3 times the 4th root of c to the 11th plus 6 I thought I was writing a c, sorry. 6c squared times the fourth root of c to the third. So let's see about reducing this. How many 4s in 11? Well, there's 2. The index stays the same. And then 2 times 4 is 8. And 3 left over makes it be 11. 6. And how many? Well, the exponent here is smaller than the index, so there's nothing left to come out. But if you notice now, I have the fourth root of c to the third in both terms, and I've got c squared in both terms, so these are like terms. So I just keep the like term part and add or subtract the numbers. Okay? Hopefully you're catching on. Easy enough. Okay? 18a to the fifth times the cubed root of 7a squared b plus 2a to the third times the cubed root of 7a to the eighth b. All right, so both my indexes are the same, but what's underneath isn't. So let's see. In this first term, there's nothing I can reduce. So we leave this one exactly like it is, 18a to the fifth times the cube root of 7a squared b. Now let's see if there's anything else I can do here. I cannot reduce, there's no such cube, even cube anyway, of the cube root of 7. Then let's look at how many how many 3's in 8? Well, there's 2. And so that gives me, when I multiply it on the outside, a to the third times a squared. When we are multiplying, we keep the base and add the exponents. B has a 1 exponent, so it's less than the index, so that stays the same. So now we got 2a to the fifth, 7. Now, let's think about how many 3's were in 8. 2 of them, so 2 times 3 is 6. That left us with 2 a's left over, okay? And now our radical parts are the same, and our a to the fifths are the same. So we keep the like part of our terms and add or subtract the numbers, and I get that. I'm going to have to go on to the next video, so we're going to call this one number 1, and I will finish up with the other examples that I have. Okay? All right.